Section: Introduction. To make the most out of large language models, LLMs, for society's benefit, it's crucial to ensure they act in ways that match what humans expect and value. The first strategy for doing this was called reinforcement learning from human feedback, which involves training a model to predict which of two options humans prefer, and then using reinforcement learning to make the model's choices align with those preferences. More recently, a new set of methods called direct alignment from preferences, DAP, has become popular. Unlike the previous approach, DAP methods update the language model directly based on which options humans prefer, making the process simpler, more efficient, and more stable. However, a big challenge with DAP methods is that they rely on feedback collected in advance, and the feedback is often based on responses generated by different LLMs. This means the model doesn't get to learn from its own mistakes during training, which can lead to problems because there's a mismatch between the data it was trained on and what it's actually doing. To address this, we're introducing a new approach called Online AI Feedback, OAIF, for DAP methods. This method combines the best of both worlds: the simplicity of DAP methods and the real-time learning from reinforcement learning from human feedback. Here's how it works. We first generate two responses to a prompt using the current model. Then we get real-time feedback on these responses by asking another LLM to predict which one a human would prefer. And finally, we use this feedback to update our model. This way, our model can learn from its own actions as it trains, avoiding the problems that come with using pre-collected feedback. We tested our new approach against traditional DAP methods and the reinforcement learning from human feedback approach, using both AI and human evaluations on standard tasks for aligning LLMs. Our findings show that our online DAP methods outperform the traditional offline versions, with human evaluators preferring our online method over the baseline, reinforcement learning from human feedback, and reinforcement learning from AI feedback methods in a significant number of cases. We also found that we could control the length of the model's responses by instructing the LLM giving feedback to prefer shorter answers, leading to shorter but still high-quality responses. In summary, our contributions are showing that our online AI feedback method can effectively turn offline DAP methods into online ones, demonstrating its effectiveness and flexibility across different tasks, and proving that we can control the characteristics of the model's output through this method. Section Summary. The section introduces the importance of aligning large language models, LLMs, with human expectations and values, discussing the methods of reinforcement learning from human feedback, RLHF, and direct alignment from preferences, DAP. It highlights the limitations of offline feedback and DAP methods due to distribution shift between the policy generating the dataset and the policy being aligned. The proposed online AI feedback, OAIF, method addresses this issue by using a three-step procedure to obtain online feedback and update the model, demonstrating its effectiveness through empirical comparisons with existing methods. Section: Direct alignment from online AI feedback. We've seen that direct alignment from preferences, DAP, methods are straightforward and don't need a separate reward model, but they rely on preference data that's collected beforehand and not in real time. On the flip side, reinforcement learning from human feedback, RLHF, methods work by interacting directly with the language model as it's being trained, but they need complex techniques to get accurate updates and a way to keep the learning process stable. To combine the best of both worlds, we've come up with a simple yet effective way to update DAP methods so they can collect data and learn in real time, just like RLHF methods. Collecting data as the model is being trained is key to making sure it aligns well with what we want it to do. Our solution to the problem of needing pre-collected data in DAP methods is to gather preferences right as the language model comes up with responses. However, getting humans to provide this feedback every time would be too costly and time-consuming. Previous research has shown that using AI to give feedback is a good stand-in for human input, especially when deciding between two options. So, we suggest using a large language model, LLM, to automatically decide which of two responses is better, right as the model is being trained. We call this approach Online AI Feedback, OAIF. Here's a quick rundown of how OAIF works. Given a starting point, the model comes up with two possible responses. Then, we use another LLM to pick the better response of the two. This method can be used with any DAP loss function that can be adjusted based on the model's parameters. A key detail in making DAP methods work in real time is how the model's parameters play a role in both coming up with responses and in calculating the loss function, which is different from how things are done in traditional DAP and RLHF methods. With OAIF, since the chosen responses are also influenced by the model's parameters, we handle the technical challenge by focusing on the gradient of the loss function with respect to the model's parameters, while not adjusting the model based on the initial response generation and feedback steps. We also explored how to make the model's responses better by tweaking the prompts used to collect AI feedback. For instance, we found we could make the model prefer shorter responses just by asking the LLM annotator to favor them. This flexibility means we can improve the model without extra computational costs, like retraining. In our experiments, we tested OAIF on 3 tasks: summarizing text, TLDR, being helpful, and not causing harm. We prepared our tests using prompts from a dataset and used 2 versions of the PaLM model for the language model and the annotator. We tried out OAIF with 3 different DAP methods and adjusted some settings based on initial tests to get the best performance. We used a specific setup for training, including the optimizer and learning rate, and evaluated the models by seeing which one's responses were preferred more often, both through automatic methods and human judgment. In summary, our approach, OAIF, offers a promising way to train language models in real time by using AI-generated feedback, combining the simplicity of DAP methods with the real-time learning capabilities of RLHF methods. Section Summary. The section discusses the bridging of the gap between DAP and RLHF methods by proposing an online AI feedback, OAIF, approach, which collects preferences on the fly for responses generated by the language model being aligned. This approach leverages an LLM as an online annotator to obtain preferences over pairs of responses, enabling on-policy learning and online learning. The OAIF method is general and works with any differentiable DAP loss function, offering high flexibility without incurring extra computation compared to RLHF and RLAIF methods. Additionally, the section outlines the experimental setup, where OAIF is demonstrated to be effective across 3 DAP methods, DPO, IPO, and SLIC, and various tasks, showcasing its generality and adaptability in obtaining online feedback for language models. Section: How effective is OAIF for LLM alignment? We're looking into how effective online AI feedback, OAIF, is for aligning large language models, LLMs, with desired outcomes. To do this, we compare methods that use OAIF, which gathers feedback in real time, with those that rely on feedback collected beforehand, offline methods. We use a method called DPO. We don't specify what DPO stands for, but it's a technique for model training, as our main example. First off, we checked how well DPO works when it uses OAIF. We call this online DPO, versus when it doesn't, referred to as offline DPO. We compared both versions against a standard method called SFT on a task abbreviated as TLDR. The results showed that both online and offline DPO did better than SFT, but online DPO kept improving over time, while offline DPO started to fall behind after a certain point. This suggests that OAIF is quite effective. To make sure our findings were solid, we repeated the experiment using 2 different systems for evaluation, Gemini Pro and PaLM 2L. The results were consistent, confirming that OAIF really does help. We didn't stop there. We also tested OAIF on various tasks, including making summaries, TLDR, being helpful, and avoiding harm. We compared the best online and offline DPO models through human evaluation. The verdict was clear. OAIF significantly boosted DPO's performance across all tasks, outshining the offline approach. This tells us that relying on pre-collected feedback can actually hinder the alignment of LLMs, while real-time feedback from OAIF is much more beneficial. Curious about whether OAIF's benefits extend to other methods, we looked into two more techniques, IPO and SLIC, using human evaluations again. Just like with DPO, methods using OAIF performed better than their offline versions, confirming that offline methods have a common problem that OAIF can solve. We also compared DPO using OAIF with two other methods, RLAIF and RLHF, to see which was preferred. Online DPO was more liked, winning 58% of the time. This suggests that using LLMs for real-time feedback, as OAIF does, is better than using fixed models, RMs, that don't update as the LLM learns. We even tried updating the during training, but it was complicated and costly, and still didn't perform as well as OAIF. One thing we noticed, though, was that OAIF tends to make the LLM produce longer responses. Since both humans and automatic evaluators often prefer longer answers, this could skew our results. To address this, we grouped responses by length and found that even when you control for length, OAIF still leads to higher quality responses. In summary, our investigations show that OAIF is a powerful tool for improving the alignment of LLMs, outperforming offline methods across various tasks and settings. Section Summary. The effectiveness of OAIF for DAP methods, compared to their offline counterparts, was examined by tracking the win rate of online DPO and vanilla DPO against the SFT baseline on TLDR. The results showed that online DPO improved performance and surpassed offline DPO, demonstrating the effectiveness of OAIF. Additionally, OAIF was found to be compatible with arbitrary DAP loss functions and consistently outperformed offline DAP methods, confirming its effectiveness as a general framework for addressing challenges in DAP methods. Comparing online DPO with RLAIF and RLHF, it was found that online DPO with OAIF was preferred over the other methods 58% of the time, demonstrating its superiority. Furthermore, online DPO with OAIF provided responses of higher quality than other methods at fixed length, validating its effectiveness in producing high-quality responses. Section. How does the size of the LLM annotator affect performance? We explored how the size of the language model, LLM, annotator influences its performance. Initially, we collected feedback using a large model, POM2L, to see if smaller models could also provide useful feedback. We conducted experiments with POM2XS and POM2S. Our findings showed that the size of the LLM annotator matters a lot. Generally, the larger the model, the better the performance of our online DPO method. However, even feedback from the smallest model, POM2XS, improved alignment performance significantly compared to the starting model. Surprisingly, this small model's feedback was almost as good as feedback learned from human input. Further tests confirmed that feedback from POM2XS was highly valued, scoring slightly better than human feedback in terms of overall quality. We also investigated how well we could control the LLM annotators by changing the prompts we gave them. Our goal was to make the LLMs provide responses that were not only helpful but also concise. By adjusting the prompts, we managed to significantly reduce the length of the responses without much effort. However, making the responses shorter also made them less helpful, although they still performed better than the baseline model. This shows that by tweaking the prompts, we can influence the behavior of the LLM annotators quite effectively, but there's a trade-off between response length and helpfulness. Discussing limitations, our study mainly focused on how response distributions shift but didn't delve into how user prompts or the core human values we aim to align with might change over time. While adjusting prompts is a flexible way to handle some changes, it doesn't address all potential shifts in user expectations or values. Moreover, we only used a small LLM for alignment, leaving open the question of whether our findings hold for larger models. Another point we touched on is the idea of self-annotating models, where the model being trained also generates its own feedback. This approach has its drawbacks, such as requiring the annotating model to be the same size as the model being trained. However, our experiments suggest that using a separate, possibly larger or higher quality LLM annotator could be more beneficial. We also considered the possibility of using weaker LLM annotators to guide stronger models, a concept we liken to the teacher-student relationship in learning. This approach could potentially allow for model alignment without needing direct human involvement, by simply instructing the LLM annotators with detailed prompts and a few human examples. Furthermore, we discussed extending our method to align models with qualitative human values, like helpfulness or fairness, by adjusting the prompts given to LLM annotators. Lastly, we considered the potential of using real-time feedback from actual users to personalize LLMs. However, the sheer volume of data needed for effective fine-tuning presents a significant challenge. We suggested that future research might find ways to make this process more efficient, possibly through techniques like low-rank adaptation, to make personalization to individual users feasible.